Welcome back, everyone, to the first session after the lunch of PEPM. And it's my pleasure to introduce Tsuyama, and he's going to talk about algebraic effect handlers.
So, hello everyone. I'm Syouki Tsuyama from Tokyo Institute of Technology. I will talk about an intrinsically typed compiler for algebraic effect handlers. In this work, our goal is to develop type-preserving compiler for source language with first-class continuations. We focus on type preservation property rather than efficiency. Previous work developed type-preserving compilers for various source language features. And we consider manipulating first-class continuations and developed a type-preserving compiler for effect handlers. We selected effect handlers as a source language facility because it is practical and can express various effects by manipulating continuations. We prove type preservation by implementing an intrinsically typed compiler using the dependently typed language Agda. Pickard et al. Developed the intrinsically typed compiler for language with exceptions. We extended it for effect handlers. Intrinsically typed compiler converts between intrinsically typed AST, which only represents well-typed terms of implemented language. The advantage of intrinsically typed compiler is that type-checked definition can be regarded as proof of the type preservation of compilation. Intrinsically typed AST is designed to represent well-typed terms, but not to represent ill-typed terms. Let's look at simple AST in the Burnett language. It can construct ill-typed terms such as 1 plus 2. And this is the intrinsically typed AST of Burnett language. Data type exp receives the additional parameters of data type tie for types of Burnett. This AST cannot construct ill-typed terms like 1 plus 2. The main challenge of this work is typing continuations to ensure the safety of continuation manipulation. In the previous exception language, continuations can be only discarded. But in our source language with effect handlers, continuations can be captured and resumed. So we cannot use previous typing as it is. To solve this challenge, we incorporate a stack polymorphism for typing continuations in the target language. This technique originally proposed by Morissette et al. But we argue that the key novelty of our work is using stack polymorphism for compilation of manipulating continuations. Let us begin by looking at how effect handlers in the source language behave. Our source language is the simple language with effect handlers. Effect handlers are the generalization of exceptions and handlers. In this language, operations causes effect, and handlers determine the behavior of operations. Handler can freely use continuations bound to k. When this program is executed, the operation OP is called and the process moves on to the corresponding computation in the handler. In this handler, continuation is resumed with by the value 0. In the resumed continuation, the operation call is replaced by 0. Now, handler computation finished with returning the result value 1. Then, the return clause is executed. It returns given value as it is, so the final result is 1. Now let's see the detail of our work. First, we define the intrinsically typed AST of source language. Value and comp and handle are the data types representing well-typed values, computations, and handlers of source language. Value is annotated by value by values typed CTX and VTI representing the typing context and type of values. And comp and handle types are similar. Next, I explain our target language. Our target language is a set of instructions to the stack-based machine. Now, let's see how effector handlers is emulated in target language. I show the stack transitions resulting from the execution of the compile source term. First, the compile handler hand is pushed onto the stack. The entity of hand is a collection of compiled clauses. The execution moves to the handled computation. This computation pushes one onto the stack at first. And next, the operation OP is called. When capturing the continuation, the stack used by the continuation is cut off and bound to K together with the continuation body. Now execution moves to the operation clause. This first pushes K and 0 onto the stack. Next, the continuation resumed. At this time, stack is reconstructed by the stack stored on K. Then further execution follows, but I omit to explain. Now we know how to execute effect handlers in target language. Now let's see the typing in target language. Target instructions are typed by typing context for variables and two stack types before and after the execution. When typing resumable continuation in this method, the challenge arises. The challenge is that the input and output stack is not known when capturing continuation. For example, let's look at two cases for continuation resumption numbered 1 and 2. The shape of the stack when executing the continuation body depends on the context in which the continuation is resumed. We solve this challenge by incorporating stack polymorphism to our target language. The type of continuation body quantifies the stack at resumption large S2 and the output stack large S3. By doing this, unknown stacks at capturing can be abstracted. Finally, let's see our compiler. Compile function is the intrinsically typed compiler for top-level program of source language. The type signature of compile represents the statement of typing preservation. So we can regard type-checked definition as proof of type preservation. We define the compiler function with some auxiliary functions and type-checked all definitions. So we could prove type preservation. All implementations can be found on the GitHub linked in our paper. Our future work is to prove semantic preservation properly. We think this can be achieved by extending compiler calculation method used by Picard et al. And then we are interested in type preserving compiler for other continuation facilities, such as shift 0, reset 0, shadow handlers, and so on. Finally, we are making type preserving optimization compilers based on continuation usage. To achieve this, we plan to extend the source language with the notion of multiplicities, which represent how many times variables is used. So, in the summary, in this work, we implemented an intrinsically typed compiler for effect handlers. We incorporated stack polymorphism for typing continuation. As future work, we plan to prove semantic preservation. investigate other continuation facilities and making type-preserving optimization compiler based on continuation usage. So this is the end of my presentations. Thank you for listening.
Do you have any questions?
Thank you for the talk. Could you please show the type preservation function signature that you had on the slides earlier? So from, no, sorry, this was, yeah, there's exactly
Yes.
this compile. So from this, it looks to me, therefore, that the types of values which you can store on the stack in the stack machine is the same as the types of values that you allow in the high-level language?
Yes.
Yeah, so did you think about having a stack machine which was more low-level, so the and you would have to do a type transformation? Because I would be surprised to see a real stack machine where you can represent all high-level values on the stack, right?
So
So, what do you mean by simpler?
Sorry?
What do you mean by simpler?
Like, as in, like, so I mean, so I'd expect, for example, this A on the left to be possibly some compound high-level type. And I would expect for a stack machine, the individual stack value, do you allow for the individual stack values to also be large compound types? Would you expect them possibly to be simpler types, like, for example, just primitives? And then you would have to express that you do some sort of mapping for a compound into primitives, or?
That might be possible. We are just following previous work on intrinsically type compiler for exceptions, and they're using this kind of typing.
Okay, so they're
yeah.
also doing this. Okay, so okay, this wasn't a decision that you made. Okay, so thank you.
Can you comment on this intrinsic types? Are they essential, or they just make your proof easier?
yeah, the advantage of intrinsically typed compiler is is describing how to compile, how to perform type preserving compilers with implementations and type preserving proof at the same time.
Okay. Also, can you comment on how do you deal with the bindings in your formal proof, and how much like boilerplate code proofs do you have for dealing with the bindings?
Yeah, we use for the Brown index for variable bindings. So yes, that's because the some previous work use it to implement intrinsically typed AST. So it's easy to use for to implement our AST.
Do you have any other questions? I've got one more question. So you said one of the basically future work things is to have also kind of show the preservation of semantics. Do you already have an idea how you would go about this with the compiler calculation?
Yes. Compiler calculation is a method to derive compilers satisfying the semantic preservation. So incomplete. And this method derives from derives by equational reasoning, starting from the equation representing the semantic preservation. So it uses the definition of ST and source language ST and definition of interpreter.
Okay, thank you. Thank you. Otherwise, then let's thank the speaker again.